Rafa is going to talk about VFSMOD and how we might model with an example here a potential conservation practice. So Rafa.
He's muted.
All right, so that was my question. Can you hear me now? Yes.
Yes.
Okay. Thank you. So I want to thank my co-authors in this enterprise, Gary Fox from North Carolina State University, Amy Ritter, Waterborne, Stefan Reichenberger in Germany, Noel, and many others. Chris set the stage very nicely. I don't need to talk about the practice anymore because here are the buffers. He mentioned this as being an off-site conservation practice. And what I'm going to describe are quickly processes, important processes within the buffers that ultimately determine the efficiency of removal of these contaminants on the runoff. Everything starts with, we have the agricultural field here on the left of this graph. It rains. And then there is rainfall intensity, which can exceed the capacity of the soil to take that water, what we call infiltration. So if at times the rainfall intensity is larger than the infiltration capacity, then we get what we call excess rainfall, which essentially is water on the surface. That water moves down gradient with the slope towards eventually an adjacent water body, a canal, you know, a lake, a river, whatever it is that is down there. So unimpeded, the water will be entering the water body, but also, and very importantly, particulates, sediment, loose particles that might be on the surface are picked up by the runoff, and chemicals which are distributed, either dissolved in the water or attached to the sediment, will also be carried on to the water body very quickly. The timing is very important. So what we can do is put this dense vegetation, bands of dense vegetation. This is very important. And by the way, here I do not just refer in terms of processes to grass or other type of species, these types of species, but it could also be a mix of grasses, more bushy vegetation, more what we call riparians as well. The processes are similar. So what are the processes then? Well, we have this vegetation, which ultimately increases the hydraulic resistance. There is more roughness on the surface, but also, and importantly, infiltration. There are comparative studies of adjacent mature grass areas next to the same unit, soil unit, and upwards of 1 order of magnitude can be observed in increases in infiltration between the grass or the buffer area and the field because of the action of roots, organic matter accumulation, and other processes. So what we get then is that there is a delay in the flow velocity, and also there is a reduction of total overland flow, and with the reduction, why? Because there is infiltration. So with that, also dissolved pollutants start getting out of the way from entering into the water body. Now, the delay of the velocity of flow is very important because remember, transport capacity of sediment is a function of velocity. So if velocity goes down, things start settling. The particulates in the surface water start settling down. So we start getting effective removal of the sediments at the entry, typically of the buffers for coarse particles. Others will move through far into the buffer. We'll talk about that later. But ultimately, the deposition of the sediment also means that the sediment-bonded contaminants get deposited on the surface. So now we have the ultimately under ideal conditions, we get reductions of runoff, which means dissolved constituents, reductions of sediment, which means sort constituents. So to what extent these processes work? Okay, and ultimately from a mitigation, risk mitigation or management perspective, what should be the way that we use these buffers? And we have different approaches with trade-offs. So we could go with the one size fits all. So everybody uses this size of buffer everywhere. It doesn't matter where, what we call this political design. We could also go into, based on empirical data, maybe we get ideas of reductions assigned to this practice, and then we can use these fixed coefficients, some sizes fits all. And again, the limitation here, of course, is how representative was the original empirical data for all other conditions where it's later applied to. And then we can go into the higher tier, which is we need to incorporate dynamics of land use, flow, sediment, chemical transport, what we are going to call quantitative mitigation, and we are going to advocate for in this presentation. And importantly, on the two arrows on the side, you have this trade-off between simplicity and transparency. And of course, we know this principle, Occam's principle, the double sword, simpler is better, but remember, only if it works. So it's simple, realistic enough to represent these conditions. And if not, we are going to have to go into these more detailed descriptions. So is the size of the buffer, understanding the distance from the edge of the field to the water body sufficient, is a good predictor of the efficiency. So in this graph, we have on the x-axis sizes, distances from the edge of the field to the water body that are occupied by the vegetation, or in the y-axis we have the reduction of pesticides. And so 0 would be no reduction, 100% would be all is reduced on the buffer. And you can see that across all sizes, when aggregating over a large database of field studies, we can find that pretty much you can find any reduction regardless of the size. So size alone is not a good predictor. So what else is going on there? Well, in this study, Reichenberger shows that although the long-term efficiency expected on the buffers under good conditions might be around 50%, there is large variability, okay? And that is driven by the specific hydrological, sedimentology, and also pesticide characteristics. So, and also that the important processes in the buffer are the ones I mentioned before: infiltration, sediment deposition, and then the pesticide characteristics. And the three need to be considered. So, in this sense, VFSMOD was built on these mechanistic components, where again, we get the flow, we get the sediment, the deposition of the sediment, the infiltration in the buffer. We also get rainfall and also lateral flow with chemical and sediment coming from the field before it enters on the edge into the water body. So by calculating all these processes and the dynamics between them, we can get realistic assessments of the reductions of the buffer under specific conditions. So we need to consider all these processes together, dynamically coupled, to be able to quantify the efficiency of these buffers. So this is what VFSMOD, again, is a public domain model that is distributed. I put here the website, and later on I think you will have the slides available, and you can also go and look for more information here. There is a wide body of publications also on application testing, development of the model. The model has two main components, the overland flow and the sediment filtration module. They are always active when you run the model. And then there is a user-selected component, which is the water quality or pollutant transport, which includes pesticides. And then, so on the overland flow is coupled with rainfall and infiltration processes. The sediment filtration feeds from the overland flow, and then from there, the partition on the chemicals follows. So on the overland flow, we have a numerical solution of the overland flow equations. In this case, a kinematic wave approximation is done on numerical methods, a finite element solution. The important thing about this is that it considers a dynamic mass balance between all the components: rainfall, lateral flow, infiltration, and that it solves that equation across field characteristics. So along the buffer, you could have these similar slopes, roughnesses, bolt spots, and things like that. Importantly, you can also run conditions that we have been discussing here in this workshop, including flow concentration. And the flow concentration could be the top of the, on the right, you see three scenarios of overland flow. One would be just ideal, sheet flow on the field, sheet flow on the buffer, highest efficiency. You could also have concentration in the buffer, which typically will be the result of low maintenance, aging of the vegetation, ultimately channelization through the buffer. And you could also have an already existing flow concentration in the field that cascades into the buffer, continuing the flow through. Clearly, the reductions expected under flow conditions will be lower than under sheet flow, and maintenance should be in place to precisely increase the efficiency of these buffers. On the infiltration side, it incorporates a Main and Larson, a Greenamp, a physical model for infiltration coupled to the overland flow equation under deep water table conditions or no water table conditions. But interestingly, I think for this workshop is also the new algorithm that we developed for shallow water presence. So physically, in the presence of a shallow water table, under initial hydrostatic equilibrium conditions. Soil moisture distribution in the profile is affected by the depth of the water table. And from there, there is a limitation to infiltration, which means that the partitioning of the surface-subsurface flow processes gets shifted so that there is more flow on the surface, more velocity, less deposition, more transport through, and ultimately reduction of efficiency when a shallow water table is present. And to the extent that that effect is there will depend on the depth of that shallow water table. This might be of interest on wetland assessments as well. This component was validated in the lab with soil boxes that we could control the depth of the water. Gary Fox did this analysis and compared with model results. We also applied to field conditions, in this case in France, under flatlands, which prone to shallow water table, more slopy lands with coarser soils, which had less. And then this graph here essentially captures the story. The x-axis on the graph on the left-hand side is the depth to the water table. So 0 will be right on the surface, deeper will be deeper in the soil. And then the y-axis, dq will be reduction of runoff, de, reduction of sediment or erosion coming into the buffer. And finally, a reduction in pesticide, dp. The two lines on the bottom are for the two sides that I mentioned before, but the gist is that as the water is on the surface, 0, you get very low reduction in runoff, as you would expect. No water goes in the soil. But as you start going deeper into the ground, you start increasing the reduction of runoff until you get to a point where no longer there is a sensible reaction to that or impact of the water table. Simply, the surface and subsurface processes get decoupled, and then everything is depending on excess rainfall, as we mentioned before. In the center here, we have 3 lines for different types of chemicals, more salt, less salt, and you can also see that there is sensitivity to this presence of shallow water table from about 50% to upwards of 90% on the best condition for this particular site. So there is indeed sensitivity to trapping efficiency as incorporated by the shallow water table conditions when there is a shallow water table condition. Now, in terms of sediment, the model uses what is called the University of Kentucky grass earth model, which essentially was a physical sedimentology model that essentially describes 2 movements of 2 different types of particles, what we call coarse particles, which are essentially too heavy to float, and they roll. And those are very effectively trapped on the entry of the buffer, and they create those sediment wedges on the front of the buffer. And then the finer particles sort of get suspended and deposited on the tail of the buffer. So how big should the buffer be will also be depending on the sediment type. When you get finer sediment, you will need tails, longer filters to be able to capture those. When you get mostly coarse sediment with a very narrow buffer, you could do away. So, and then when it comes to pesticide trapping, again, we go back to the principles. We need to consider here on the top, on the left, hydrology, sedimentology, and in essence, reduction of runoff, reduction of sediment, and then the chemical characteristics of the pesticide, which are sorption, distribution between the liquid and the solid phase, given either by KOC or KD, and then the sorptive phase, organic carbon and clay in the sediment. Different approaches. One of them, the first one that was incorporated is a semi-empirical equation which builds on these ideas, these principles, but requires parameterization on the basis of a large data set. 244 points in the latest fitness. The idea is by broadening the base, you can get more representative results. And in this case, you depend on 5 regression coefficients, this AD. Now, there is another equation that we developed and tested, and I'll show the results later, requires no regression parameters, simply is a mass balance on the surface between liquid-solid phases, incoming, water, rainfall, and so on. And then finally, the question is, what happens to the pesticide after it is being deposited in the buffer? And here, the VFSMOD incorporates a full degradation, carryover and remobilization component. In essence, the pesticide comes into the buffer, is deposited along the buffer. This is the trapped mass here in the center. And then there is an output, which is the fraction that goes into the water body, hopefully reduced. And then what happens to the trap mass? Well, part of that, of course, gets infiltrated. Part of that gets sorbed to the sediment on the surface from the last event. Of the fraction that gets infiltrated, part of that, what we call the mixing layer, is available to future runoff events on the sequence, on the time series. Deeper, a fraction of that goes below the mixing layer and is subject to soil degradation, but is no longer available on the surface transport. And then of the mass that is retained on the sediment sort or in the mixing layer, it goes daily degradation time steps based on time, half-lives, and for example, in the European Union, the focus approach also is depending on temperature and moisture content on the daily time steps. At the end of the day, between the two events, there is a residual amount, and that amount is redistributed between the solid and liquid phases, both on the sediment layer as well as the mixing layer, and then the solid phase stays and then participates on redistribution on the next event. The liquid port water actually is upwelled and added to the incoming mass from the next event. So in this case, we can get a full picture of what are the residues, how much of that is affecting next events, and so on. So the big question would be, can we test a fairly sophisticated model like this one? The answer is yes. There have been people that have been compiling field studies from different sources, academia, industry, other sources, and then they constitute a very nice data set to be able to test with real values. The nice thing about this is just a representation of all the data in all these studies, two databases. The nice thing about it is that there is a wide range of conditions in these studies that give us from 0 to 100%. So it is very good to test models because then we can actually see, we can predict low and high depending on the conditions of these studies. It also has a nice partitioning between what we would call high and low sorption products. Below the KOC, low KOCs would be typically more dissolved, more in the liquid phase. Higher would be more in the sorb. But there are a good subsets within the database to test also the ability of the model to do across. And in here, we are comparing the performance of reduction. Again, on the x-axis, we have the observed values from the studies. On the y-axis, we have the predicted, VFSMOD predicted reductions. On the top here, you have the Nash and Sutcliffe, or the degree of agreement with the one-to-one line, perfect agreement. Higher numbers, typically 0.65, might give us better predictions, or essentially an efficient model. And I have here on the first one on the left, all products, regardless of the KOC. On the center, low KOC or mostly dissolved, and on the right, highly sorbed. And you can see on the top that the efficiencies are high across all the cases. And interestingly enough, the fully mechanistic equation, which is this the cross here, the plus sign here, is actually efficient and doesn't require any empirical coefficients. Another interesting thing about model testing, Mike Winchell, which is with us, led this study that was commissioned by EPA, looking at potential candidates to look at mitigation models for buffers that could be used in the regulatory process. They pulled together models that had capability to incorporate buffers, Apex, Prism buffers, SWAT, REM, VFSMOD. SWAT was discarded early on because of the scale. It was not at the field scale. And then field models were selected for this. They were different independent teams were given inputs, no outputs. This is what is called cold testing. So not knowing the results, see what you get, and then the results are brought back into the table and compared to the real values. And here are the mean absolute errors with respect to observed values, or if you want in the bars. Higher bars means more error across the three runoff, sediment, and pesticide reduction outputs. And VFSMOD came up as the lowest errors across all these. So very efficient in terms of predicting for these conditions that we talk about, which were in the US as well as Germany, one of the studies. So many others testing has been done. Here is a reference that you can go and look at. And finally, to wrap up, so we have potentially we could frame this question of mitigation, in particular buffers, to do these buffers reduce runoff, or perhaps the more interesting question, what are the field conditions that actually limit the efficiency of these buffers so that we can consider those in the risk assessment or management process. And I submit that the second one is more interesting and really the one that has been driving our research for years. I list here a number of these potential factors like surface channelization that I mentioned before, flow concentration, timing of the application, shallow water table conditions, what happens to pesticides in the long run with the residues and others, including preferential flow, soil drainage, and other impeding conditions. So I leave the references here in case you are more interested about details. One plug on maintenance, I already discussed that. Maintenance is critical. We need to keep these buffers at nominal conditions, which means at times that we are going to have to reset these buffers. These are not long-term practices. They have to be continuously maintained by mowing, avoiding compaction and things like that, and of course reset every so often. There are some evidence that these buffers, if well maintained, they could even increase somewhat their efficiency. There are also evidence that not maintained, they will lose their efficiency. And finally, it's important to consider all these drivers, physical processes, to be able to understand true efficiency or realistic efficiency of these practices. For this, we are going to need to incorporate them into our tools to be able to incorporate the richness of the scenarios for risk analysis and management. VFSMOD has been developed and tested for this purpose and found to be efficient in the process. Always remember, almost are wrong, some useful. We hope that VFSMOD can be useful in this process. And finally, also the second rule, which is GIGO, garbage in, garbage out. We need to be able to incorporate good inputs to get realistic outputs. So with that, thank you very much. And if there are any questions or time, I can entertain.
Rafa, thanks. Very informative. So we do have time for a few questions for Rafa.
Rafa, this is Mike here.
Hi, Mike.
Really neat presentation, as always. The shallow water table condition, is that a static condition or is it dynamic if you're running VFSMOD in sort of multi-event?
Yes. So for the event, we consider it to be the average depth during the event. Remember, the time is very short. So I think considering fixed per day is acceptable. And now, what we can do from event to event is just follow this time series of water table as described by, that is a good question, described by what? So we go back to in the schemes that we are putting together. I'm working right now with the SWAN tool in the European Union for higher tier, step 4 tier assessments. And we can use the water table that is incorporated in the aquatic model on the mass balance that they do, the fluctuation of that, in this case is TOXWA. In the EPA would be BVWM. So we have a reference there, and then we make assumptions on what is the overboard, how deep is the canal with respect to the surface, and then we just watch the variation. So daily we can adjust the time level, the distance from the surface to be able to calculate the impact for those. So for days where the water table is deep enough, there is no effect. For days where the water table starts coming into the critical, that sensitive region, then it is incorporated. And what we are proposing, actually, the way that it's going to be automated on SWAN is it will run all in parallel. So no buffer with and buffer without when the user requires water table. So we can do a comparative analysis between the effects of that potential factor.
Great, thanks.
Thank you. Bye.
Another question for Rafa, and I will get ready to start my slides here in a moment. So we've got time for another one.
So, Rob, it's Pat Havens. We've been talking all this week about about tiers and so on, and you mentioned the these sort of constant coefficient reduction approach as the simplest and perhaps most expedient way to do so. So, in your view, is there still utility in having those before you have to go to a more computational, process-based sort of approach, within a regulatory framework?
No, absolutely. I believe so. Again, the concern on the empirical, the fixed factors that they are called, for example, the European Union has these L and M factors, they are called, And if you look at how they were derived, the base is very small. So I think it was like 16 studies, 36 studies for water sediment. Right. So it's hard to believe that they can be representative. But I still believe that there is an improvements over that, particularly incorporating more studies, could be a basis for a lower tier, maybe a step 3 on the European Union. And then if there is concern, then we can up tier with a quantitative mitigation, which is the approach that the VFSMOD offers. So I think there is still space for these approaches, in a tier approach, understanding always that lower tiers are typically, less descriptive, and as you start going up, you can incorporate the more refined technology. But yes.
All right, thanks, Rafa. I think let's
Thank you.
thank you and appreciate it. Great presentation, great information.